right, good morning, everybody at home. Can I get a thumbs up that you hear me and see the board okay? All right, guys, we are starting section 7.3. So coming off of the inverse trig functions, and now we know how they work and what they are capable of doing, now we're going to start solving trigonometric equations. So the inverses are definitely going to help us solve trigonometric equations because they're going to undo sine functions and cosine functions and whatnot. However, you're going to realize there is a very big problem with the inverses and the fact that they are very limited in what angles they can tell you. So we are going to use the inverses, however, not today. We have to kind of get used to solving these equations. And if they ask you to solve them and find exact values, or if it's a special ratio, you wouldn't use your calculator anyway. So we won't need the inverses yet. However, just keep in mind that they are limited in what they're going to be capable of telling us, okay? All right, so if we're going to solve trigonometric equations, first of all, I need you to remember that the trig functions are periodic, right? They repeat themselves. After so many inputs go in, the exact same ratios start to come back out, right? You plug an angle in, you get a ratio out. So after so many angles go in, you create one sine curve. And then different angles go in, but the exact same sine curve is created again. So I need you to remember that because they're repetitive, there's going to be a lot of angles that make these equations true, okay? So let's try it. So if you remember, to make one cycle of the sine wave, you had to go from 0 to 2 pi, right? So that was its period. That was the amount of inputs it took to create one sine wave. And then cosine. Cosine also took 2 pi radians to create one cosine curve. So it had a period of 2 pi radians. So guys, after 2 pi radians go in, the exact same ratios come out. So every 2 pi radians creates another set of angles that are going to make these equations true. But tangent was different. Tangent, because of his restrictions in his domain, he actually started to repeat himself faster. Tangent only took from negative pi over 2 to pi over 2, which is pi radians, to create one of his cycles. So the tangent function had a faster period, and it took less inputs to create another tangent curve. All right? And then the reciprocals behaved the same way. Cosecant, secant, and cotangent had the exact same periods, okay? So let's think about this. Before we start solving some equations, let's think about a really little one. Guys, if I said, use the graph of the sine function, so let's look at the sine function right here, right? We said he had a period from 0 to 2 pi. So here is one, oh, I missed it really bad. My hand covered it. Here is one cosine curve, and then it just starts to repeat after that. Use the sine function above to think about the solutions to the equation sine theta equals 1/2. If your job was to find all the angles that have a sine ratio of 1/2, well, guys, look at his graph. It goes 0 to 1. So 1/2 is like right there. So look at all the points that have a y coordinate of 1/2. I mean, obviously it continues because it's repetitive. So technically, if I asked you to find all the angles that have a sine ratio of 1/2, well, this angle has a sine ratio of 1/2, this angle has a sine ratio of 1/2, this angle has a sine ratio of 1/2, this angle, this angle, this angle, this angle, it's infinite. There are infinitely many angles that you could plug into the sine function and make a ratio of 1/2 come out. So just know, if you solve a trig equation, there's infinitely many angles that are going to make that equation true, okay? Therefore, since the trig equations are periodic when solving trig equations, if the domain is not restricted, if they don't tell you a specific interval of the graph to look at, then there are going to be infinitely many angles that satisfy that equation, okay? All right. So some of the equations that we solve today, guys, they're going to have infinitely many answers if they don't restrict the domain. But if they do restrict the domain, and normally when they restrict the domain, guys, they do 0 to 2 pi. Like one rotation around the unit circle is what they ask you to hone in on. What angles make the equation true now? If the domain is restricted from 0 to 2 pi. So guys, now you'd only have to look at one sine curve and find the angles that make this true. So look at it again. If you are only looking at one sine curve, not all of them, How many angles make the equation sine theta equals 1/2 true now? Well, guys, now on one sine curve, there's two angles that have a ratio of 1/2. So on one rotation, on one restricted domain 0 to 2 pi, now there's only two angles that make this equation true. Now there's a finite, a countable number of answers that are going to make this equation true. All right? So we have to pay attention to whether or not they have restricted the domain or whether they have not restricted the domain. Because if they didn't, we have infinitely many answers, and we have to be able to write that and show that. Or if they do restrict the domain, a lot of times with the sine functions cosine, in one rotation, there's two angles that make that same ratio come out. Guys, if the ratio was -1/2, -1/2 there and there's two angles on one sine curve that give a ratio of -1/2. And that all has to do with the all students take calculus. All students, the sine ratio is positive and positive. So there's two angles that get you a positive sine ratio in one rotation. And then it's negative, negative. And then there's two angles that get you a negative sine ratio in one rotation. So a lot of the times when it's restricted, you're going to have two answers, all right? Or if it's a quadrantal, 0, pi over 2, pi, 3 pi over 2, and 2 pi, those are the only ones if you're taking the sine ratio where they don't repeat, right? Think about it. In one ratio, 0, 1, -1, 0. Only one angle in one rotation had those ones, so they may not have two. All right, let's give it a whirl. Let's try to solve some trig equations. All right, so we're going to start with the ones that are not restricted. We're going to start with the ones that get infinitely many answers first. All right, so finding all solutions to a trig equation. Solve the equation right here for theta. Find all possible theta, right? They have not restricted the domain, so all theta that could make this equation true, and they want you to give a general formula for all your solutions. All right, well, guys, let's take this equation. Let's start solving it. Your job is to solve it for theta, right? Theta is literally stuck inside of the cosine function. So at best, the only thing you're going to be able to do is get cosine theta by itself. So that should be your goal. Isolate cosine theta. And just use normal solving equation rules. If I want to get cosine theta away, move what's not attached away first. So let's add this over, and that'll leave me with -2 cosine theta equals -4 root 2 plus 3 root 2 is -1 root 2. All right, keep going, get cosine theta by itself, divide both sides by -2, and you end up with cosine theta has to equal root 2 over 2. Well, guys, this is where the inverse would come in handy. However, you should be good enough to know, wait a minute, root 2 over 2 for the cosine function is one of his special ratios. This is going to be a special angle. If you did inverse cosine both sides, he'd only be able to tell you one answer. But we already saw there's probably infinitely many, if not at least two, in one rotation, angles that make this equation true. So even if you did use the inverse, number one, it's going to give you the decimal answer. We don't want that. And it's not going to give you all the answers to this equation. It could just get you started. So I would prefer, especially when it's a special ratio, let's use our minds. Let's not use the calculator. All right, so guys, the cosine of what angle has root 2 over 2 as his ratio? If you have to, draw your special triangles. They should always be on your mind. Keep the unit circle handy for your quadrantals. And then if you still have a picture of a unit circle, you're literally looking for what angle had an x-coordinate of root 2 over 2, because we know the cosine of an angle is represented by the x-coordinate on the unit circle. All right, so guys, the cosine of what special angle had a cosine ratio of root 2 over 2? Well, it must be something over here. Cosine 45 would be 1 over root 2, which would rationalize to root 2 over 2. So guys, we're definitely dealing with a pi over 4, some multiple of a 45-degree angle. So think about this. Let's think about it in a one rotation sense. All students take calculus. Where would the cosine of an angle have given you a positive ratio? All angles give you a positive ratio in quadrant 1. and only the cosine ratio is positive for an angle in quadrant 4. So you know if you're going to have a cosine of an angle that is positive root 2 over 2, it's a quadrant 1 and a quadrant 4 angle. Okay, well, we got to figure out, well, if it's a 45-degree angle, what multiples of 45 or pi over 4 are you sitting at in quadrant 1 and quadrant 4? So guys, what's this answer? Theta would be who here? In quadrant 1, who's the multiple of pi over 4 in quadrant 1? Pi over 4. So pi over 4 is definitely an answer to this equation. All right, but then what multiple of pi over 4 are you sitting at in quadrant 4? Guys, remember, all the way around is 2 pi radians. So in the world of pi's over 4, how many pi's over 4 make 2 pi? 8. So if that's 8 pi over 4, and you're 1 pi over 4 before that, sitting in quadrant 4, what angle is that really? That is 7 pi over 4. Okay. So guys, those are the two angles in one rotation from 0 to 2 pi that make this true. Well, guys, they didn't restrict it. They want all possible theta. So now remember, these are periodic functions. A period away from this angle, it creates the exact same ratio. So now all you have to do is add the period onto these angles to start landing in the same spot on the next cycle. So what was the period of cosine? 2 pi. So add 2 pi to this, and you're going to get another answer. Add 2 pi to that answer, you'll get another answer. Add 2 pi to that answer, you get another answer. So we would write this as the general formula would be pi over 4 as an answer, and then any angle 1 period away from him times k revolutions. And the same thing here. 7 pi over 4 is definitely an answer to this equation. You rotate all the way around again and land in the same spot, that's another solution. You rotate all the way around again and land in the exact same spot, that's another solution. So add a period to him, and there's another answer. So add 2 pi to this as well, and then times k revolutions. So those would be your answers if you didn't have a restricted domain. These are the answers that make it true for one rotation, and then you just have to add the period times k revolutions onto it. Now, correct me if I'm wrong, if it's multiple choice, sometimes it writes 2k pi. I don't know. I always write 2 pi k for me, but it means the same thing. All right, so that's what you would write for a general formula. Now, if you do the homework, it only has one answer box. So you're like, wait a minute, which one am I typing in? I think it normally says, if it's got an answer like this, it says, write it for the smaller angle. Obviously, pi over 4 is a smaller angle than 7 pi over 4, so I believe this is the one they would ask you to write in the answer box as the general formula one. All right, and then sometimes it says, all right, now you've written a general formula, now I actually want answers. Get me answers if k was 0, 1, 2, 3, 4, or 5. Well, guys, all you'd have to do, though, if k was 0, that would be 0, pi over 4 is your answer. To get when k is 1, you'd have to add 2 pi on. So add 2 pi to this, and remember, 2 pi is 8 pi over 4. So 1 pi over 4 plus 8 pi over 4 is 9 pi over 4. So that would be another answer because it's a period away from that. Add another 8 pi over 4 on, there's 17 pi's over 4. There's another answer that you could list. Add another period on, add another 8 pi over 4, there's 25 pi's over 4, right? So that would be like k is 0, k is 1, k is 2, k is 3, and so on. And just keep adding that period on. And you can also minus the period, right? Take pi over 4 and minus 8 pi over 4, and you get negative 7 pi's over 4. And guys, negative 7 pi's over 4 is literally right there at the same angle that pi over 4 landed at. All right, so that's all you'd have to do is just keep adding the period on and on and on to create actual answers. Because I think they do. I think they make you write a formula, and then they make you list some actual answers. Just keep adding that period on. Does that make sense? Is everybody okay with that? Yeah? Okay. All right, let's go to another one. So here's another equation where they have not restricted the domain. They want you to give a general formula for all the solutions, find all possible theta. Well, guys, remember, sine and cosine have a period of 2 pi. So you'd have to add 2 pi onto your answers to create more answers. Tangent has a different period. He has a period of pi. So you only have to add pi radians on. He actually repeats faster. All right, here we go. We're going to solve this for theta. Theta is stuck inside of the tangent function. At least get tangent theta by itself and divide by 3. So now the tangent of what angle equals root 3 over 3. Now again, you could inverse tangent this. However, it's only going to be capable of telling you one angle, and it's going to give it to you in decimal form. I want the exact answer. Root 3 over 3 is a special ratio as far as tangent is concerned, and you guys should recognize that. All right, so guys, think about this. In one rotation, all students take calculus. The tangent of an angle has to be positive root 3 over 3. The tangent of an angle in quadrant 1 is a positive ratio because all ratios are positive for angles in quadrant 1. The tangent ratio gets you a positive ratio for angles in quadrant 3. So there is an angle in quadrant 1 and quadrant 3 that make this equation true in one rotation. So guys, let's figure out who it is. The tangent of what special angle? Is it a pi over 6, a pi over 4, a pi over 3? It's not a quadrangle. It's in one of the quadrants. Who is it? Go to your triangle. Who had a tangent O over A of root 3 over 3? Well, guys, 30 would be 1 over root 3. Rationalize that. That's root 3 over 3. So it's definitely a multiple of pi over 6. So there's a multiple of pi over 6 in quadrant 1 that makes this true. And there's a multiple of pi over 6 in quadrant 3 that makes this true. All right, so that means theta could be. Well, guys, who's the answer in quadrant 1? What multiple of pi over 6 lands in quadrant 1? Pi over 6. And then what multiple of pi over 6 lands in quadrant 3? Well, guys, in the world of pi's over 6, if that's pi, then this must be 6 of them. So who's the one that's 1 pi over 6 past it? 7 pi over 6. Okay, so those are your two answers. Now, because they didn't restrict it, we have to give a general formula. So I could land at this angle plus the period away from him is another answer. And what was the period of tangent? Pi times k revolutions. And the same thing here. If he's an answer, a period away from him is another answer because it'll land in the exact same spot. So what's the period of tangent again? Plus pi times k revolutions. Okay? And again, the cool thing about tangent is because his period is so quick, guys, look at this. If this is pi over 6, 1 pi away from him, 180 degrees, it lands you on that second answer. So here, I could create an entirely new list of answers by adding 2 pi to him. This one, as long as you add it to the first angle, he's going to pick up all the angles that were the second angle's answers anyway. So you only have to really add the period to the first angle that you get because his period repeats so much faster. All right, so let's say they wanted you to find a few angles now when k is 1 or 0 or 2 or 3. So take pi over 6, your first answer, and let's add a period onto it. Add pi to him, which is 6 pi's over 6 when you get a common denominator. So pi over 6 plus 6 pi over 6 is 7 pi over 6. See, it lands on the next angle's answer. It's always going to pick up the next one because his period is so fast. Add another 6 pi over 6, and you get 13 pi over 6. That's an answer. Add another period, another 6 pi over 6, and you got another answer to this equation. Add another period, another 6 pi over 6, and you got 25 pi's over 6. And you can go in the negative direction. Take pi over 6 and minus a period from him, and you get negative 5 pi over 6 is an answer to that equation. So again, there's infinitely many, and all you have to do is keep adding a period to create more answers. All right, but again, if they ask you to write a general formula, I'm pretty sure the directions are going to say, write a general formula for the smaller angle. So this would have been the one that you had to type into the answer box. And then this would have been the one you had to type into the answer box for the smaller angle. I'm pretty sure is what it says. Okay? All right, luckily for the most part, they really don't make you solve too many trig equations that aren't restricted. If they want you to find all possible theta, it's usually only for a couple questions. The majority of the equations will have a restricted domain, which are easier to solve, or at least easier to write the answers. All right, so let's try a couple of those. And again, you should not need a calculator today. We should not need the inverse functions. They're not going to be capable of getting us all the answers, and they're not going to be capable of getting us the exact answer. All right, solve each equation. Now, guys, now they only want angles from 0 to 2 pi that make this true. So in one rotation, what are the angles that make this true? Notice they let you include 0 as an answer, but not 2 pi. All right, here we go. Let's start solving first sine theta. Let's minus the root 3 away. And let's divide by 2. Okay, so we have to figure out what angles, when you take the sine of them, have a ratio of negative root 3 over 2. Well, guys, it's the sine, right? All students take calculus. The sine of what angle gets you a negative ratio? All students mean that the sine of an angle is a positive ratio in 1 and 2, which means it must be a quadrant 3 and a quadrant 4 angle that make this true, because that's where the sine ratio is negative. These are the quadrants that have a negative y coordinate. All right, well, guys, can you think? Look at your triangles. The sine of what special angle was root 3 over 2? Was it a 30? Was it a 45? Was it a 60? It's got to be a special angle of that special ratio. Anybody know who it was? Well, if the sine of a 30 was 1/2, it must be the sine of a who that's root 3 over 2. What's the other angle in that triangle? 60. It's got to be a 60. This is definitely a pi over 3. So you have some multiple of pi over 3 in quadrant 3 that makes this true, and you have some multiple of pi over 3 in quadrant 4 that makes this true. All you got to figure out is what angles these are, and we're good to go. Theta will be, well, guys, in the world of pi's over 3, here's pi, so this must be 3 of them. Who's the one that's 1 pi over 3 past them? 4 pi over 3 is an answer to this equation. And then who's here? Who is 1 pi over 3 short of a full rotation? Guys, a full rotation is 2 pi. So in the world of pi's over 3, that's 6 of them. 6 of them make 2 pi's. So who's the one that's 1 pi over 3 short of them? 5 pi's over 3. And those are the two angles that will make that equation true. So this all comes down to knowing your special ratios of your special triangles, and it also comes down to, can you work the all students take calculus? What quadrants is this ratio positive in? What quadrants is this ratio negative in? All right, let's look at this one. Same thing, if we're going to solve this for theta, then we have to get secant theta by itself. So it's minus 6 and divide by 4. Okay. I don't mind secant theta, but I'd much rather work with an original trig function. So the secant is the reciprocal of cosine. So if the secant of the angle is this ratio, then the cosine of that same angle is the reciprocal of that ratio. And what's the reciprocal of -2? -1/2. And I'd much rather work with that. And 1/2 is one of our special ratios. So let's figure this out. The cosine of what angle from 0 to 2 pi has a ratio of -1/2? Well, guys, according to all students take calculus, where is the cosine of an angle a negative ratio? So where is cosine negative? All are positive, cosine is positive. So that means the cosine of an angle is negative in quadrant 2, and the cosine of an angle is negative in quadrant 3. So the answers to this equation are quadrant 2 and quadrant 3 angles. Let's figure it out. Guys, the cosine of what special angle was 1/2? 45, 30, 60. If the sine of a 30 was 1/2, the cosine of a 30 couldn't be 1/2. It'd have to be, couldn't be a 30, it must be who's the other angle in that 30, 60, 90 right triangle? It's got to be a 60, guys. It's got to be a pi over 3. So we are dealing with a multiple of pi over 3 in quadrant 2, and we are dealing with a pi over 3 in quadrant 3. What multiples are we at, though? All right, well, guys, in the world of pi's over 3, here's 3 of them. Who lands one right before it? That would be 2 pi over 3. And who's at the one right after it? 4 pi over 3. And you're done. And those are the two angles from 0 to 2 pi that make this equation true. Let's see if we can do the last one really, really quick. All right, guys, now you have cosine thetas on both sides. It's the same thing as if you had x on both sides of the equation. Get all your cosine thetas to one side and then move everything else away from it. So I'm going to minus 3 of them over here. That's going to get me 2 cosine thetas. Well, if I move my cosine this way, I better move everything else to the right. So I'm going to minus my 6 root 3's, which leaves me with 1 root 3. Divide by 2. And now you have the cosine of an angle has to be root 3 over 2. Okay, so guys, the cosine of an angle gets you a positive ratio. What 2 quadrants is the cosine ratio positive in? All students take calculus. All ratios are positive for angles in quadrant 1. So there's an angle in quadrant 1 that gets you a positive cosine ratio. And then cosine is positive again for an angle in quadrant 4. So there's an angle in quadrant 4 that gets you a positive cosine ratio. Now you got to figure out what special angle is it. 30, 45, 60. Is it a quadrantal? No, because that's not a special quadrantal ratio. Only zeros and ones and negative ones. Is it a 30 pi over 6, a 45 a pi over 4, or a 60 a pi over 3 that has a cosine ratio of root 3 over 2? Well, guys, if the cosine of a 60, a pi over 3, was 1/2, it must be a what that's the root 3 over 2? A 30. It's got to be a pi over 6. So there's a pi over 6 in quadrant 1 that makes this true, and there's a multiple of pi over 6 in quadrant 4 that makes this true. Who are we sitting at? Who is the multiple of pi over 6 in quadrant 1? That's pi over 6. And then what multiple of pi over 6 lands in quadrant 4? Well, guys, all the way around is 2 pi radians. So in the world of pi's over 6's, that makes 12. So who's the one that's 1 pi over 6 before him? 11 pi's over 6. And you're done. And then again, obviously the unit circle makes this really easy because here you would just be looking for the x-coordinate of an angle that had root 3 over 2 as its x-coordinate. Kind of takes the fun out of it though. All right, and again, who knows in the future if you'll have a unit circle handy, so you should know how to solve it on your own. All right, so guys, I'm going to stop there. I'm not going to get to the ones that have a period change yet. So right now, you're either solving trig equations with a restricted domain 0 to 2 pi or without a restricted domain. Are you guys okay? Is everybody okay here? Okay. At home, we're all right? Okay. All right, so guys, you do have a homework assignment. I didn't actually post it yet because I didn't know if I would get to at least here, and I'm glad I did. So I am going to post the homework, but I believe I didn't make it due until like Sunday night or something like that. I think I gave you, obviously, a few days, being today is Thursday. Tomorrow, I'll try to continue on with the solving, and like I said, we're just trying to get as much as we can done before the year cuts us off. All right. Let me double check the attendance, and then you guys will be good to go. And as always, if you have any questions, please reach out to me.